Well, hello, pre-calculus class. Sorry that I'm not with you this week, but here we are, and at least this is a substitute in the meantime. If I am willing to get onto any Zoom calls too, if you guys need that this week, so just need to have the substitute, let me know, and we'll figure out a way to make that happen if that's needed. The good news about having these this way is that I will post them to the YouTube channel, and so you'll be able to watch them even later if you need to review anything that I've gone over. So today we're going to start chapter 6 and looking at vectors in the plane. Vectors is a really important discussion because an understanding of them is crucial to any work that you will do or might do in the science of physics. So you're going to be seeing in this chapter a lot of information that will be tremendously helpful to you in any amount of physics class. So if you guys are in physics now or going to be taking physics, this discussion becomes really, really helpful. And obviously, if you've already taken physics, then you'll see why this is so important. So a scalar quantity is a quantity that can be measured using real numbers. For some examples here, if you take the mass of some object, you might find it to be 12 kilograms, or the length of something, or the density of something, the speed of something, the volume of something. These are all scalar quantities. There's a unit, there's some sort of measurement, and then a unit that is attached to that in each of these. The difference when it comes to a vector quantity is that the quantity has to be described both with a number and a direction. And the most classic examples of these are things like forces and velocities and acceleration. In each case, you not only have an amount of force, but you have the direction in which the force is pushing or pulling, or which direction it's going. Same thing to be said for velocity. Speed is just speed, it's just a scalar, but velocity is a speed plus a direction. So, for example, if you're on the road and you see a speed limit sign, it doesn't matter if you're traveling this way or this way on the road, you can't exceed that speed limit. They don't really care about the direction. I guess as long as you're in the right lane at the right time, you're okay. But velocity involves also a direction. Same thing to be said for acceleration. So it's not only the measurement and the unit, but also the direction of the acceleration, such that you could be accelerating or decelerating, right? Okay, so you're going to see charts like these, and so this is kind of like the classic way to show a vector. Here we have what's called the tail of the vector. This would be the head of the vector, and so you can see that it has an amount, but it also has a direction. So that's the crucial element about vectors. It's not only an amount, but also a direction. And if we were to describe this, we could say that it goes from point P to point Q. Well, we could then give the measurement of how far this vector travels in the x direction and how far it travels in the y direction. So there's the tail and there's the head. So the vector is notated PQ because it has a length of PQ, but it has the direction of PQ ray. Note here what we normally do is we just write, it's like as if we're writing an arrow over the two letters, where the tail sits over the first point, the P here, and the head of it sits over the second point, which is the Q. And notice that we write it like this. That's the typical way that vectors are drawn to distinguish it from either a line segment or a ray. So you can see it either like this, PQ, or sometimes you'll see a really bold little letter like this for V. That can also stand for the vector. Sometimes it's hard to see bold case if you're writing on paper. So instead of that, sometimes we'll just write V with, again, that same little half arrow head over it. Another way that we can denote the vector is we can say how far it travels in the x direction, and then comma how far it travels in the y direction. So we could, again, find that a and b value by subtracting, here's the x2 and the x1. We could just subtract x2 from x1 to get a, and we could subtract y2 from y1 to get b. All right, so let's look at example 1. Given P is 4, 2 and Q is 1, -2, express PQ in component form and draw an equal vector in standard position. All right, so the first thing we do is we need to find both point P and Q. So for P, we're going to go over 4 and up 2. And then for Q, we're going to go over 1 and down 2. And there's our 2 points. And then we just draw the vector from P to Q. All right, and now we just see what's the difference in the X and the Y direction to get the components. So in the X direction, we can just take X2 minus X1, and in the Y direction, we'll take Y2 minus Y1. So we take in the X direction, we take the 1 here, and we subtract off the 4, and we'll get -3. And then in this one, we take -2, and we subtract off a 2, and we get -4. Note here, we start from the head of the vector, and we subtract off the tail of the vector, okay? You could also notice that you're traveling this direction, which is the negative direction for a -3. And then you see we're traveling in this direction, which again, down is the negative direction, would be -4. So we can also get at it that way. So -3, -4. And then we could just reposition this vector. We could just go over 3, down 4, make a dot, and then draw the vector from the origin down to that spot. That would be the standard position for the vector, where we've just moved it where the tail sits at the origin. That's the crucial matter to know that it's in standard position. Now we can also then show the not only the magnitude of the vector, but we can also show the magnitude plus the angle measurement of the vector, theta. So standard position for the angle is measured from the x-axis, which you're used to doing when we were talking about the unit circle and radians and all of that. So you're kind of used to this being 0 anyway from those discussions. Remember when we were talking about bearings and stuff, remember the 0 direction is the north direction, but not in this case, not in the radian measurements that we're doing. So 0 is along the x-axis. We travel around like this to find that angle. And in this case, we could discover what this reference angle is first, this alpha angle is, by we could do like arctangent, right, of -4 over -3 to find what alpha is. And then we would just add 180 to that, right? Because from this point to this one, it's 180 degrees. By the way, just to take note here, again, we're going to be dealing mostly in degree measurements again. So make sure when you're using your calculators on these things that you are in degrees, because in most cases, we're going to be dealing with degree measurements. All right, so if you're trying to find the magnitude and direction of a vector that's in the form of a comma b, the magnitude is just going to be a squared plus b squared, take the square root of all of that, right? So remember, if we had a vector that's like traveling like this, let's say, and we had an a and a b, well, we could find c by just doing a squared plus b squared and then taking the square root of it from the Pythagorean theorem. And then, as I said before, we can find that reference angle by doing arctangent of just b over the absolute value of b over a, and then just looking at where it is on the Cartesian plane and discovering if I need to add 90 or 180 or 270, depending on where it's landing in there. By the way, some older math books have designated the vector's magnitude with double bars. So instead of it being just single bars, they did double bars, but typical form today is to just show it like this with just single bars around it. That means the magnitude of vector v. And as I said before, depending on what quadrant the vector is in, if it's in 1, 2, 3, or 4, we just end up finding that alpha angle, which is that reference angle. If it's in quadrant 1, that's the angle. If it's in quadrant 2, we're going to subtract that reference from 180. If it's in quadrant 3, we're going to add it to 180. And if it's in quadrant 4, we're going to subtract it from 360. But again, I think it becomes apparent once you draw it onto the coordinate plane. And when you find that measurement, you should be able to look at it and discover what we need to do with that reference angle in reference to the total angle that we need to denote. All right, so example 2 says state the magnitude and direction of PQ in example 1. So here it is. So we just going to first of all do our a squared plus b squared and take the square root of that. So 16 plus 9 is 25. 25 square root of 25 is 5. So we know that this is the 3, 4, 5 triangle. And then if we're trying to discover the angle measurement of alpha, we're going to do the arctangent of b over a, right? So that would be this guy over this one. So it would be -4 over -3, or 4 over 3. And when you take the arctangent of it, you get 53.1. But remember, that's this measurement. We need the total for theta. So in this case, since we are in the third quadrant, we're going to take that measurement, add 180 to it, and get 233.1 roughly degrees. Okay, now if we're going to sum two vectors together, the way that you do this is you place the tail of one vector at the head of the other. The resultant is the sum of the two vectors, right? So if I want to add vector u to vector v, then all I do is I take v, let's say that these were both started at the origin, I just move the tail of v to the head of u, and then I draw a line from the first tail all the way to the head of the other one. And that's going to be the resultant vector. We call it r here if we wanted to. But that's going to be the resultant of the things added together. So a resultant vector is just whenever we sum two other vectors, like in this case, u and v. You'll see a lot of this kind of notation where the measurement of u, which would normally you'd think about this being like x comma y. A lot of times we'll just write that as u1, u2. And then for v, again, this would be the x coordinate and the y coordinate. They'll just mark them as v1, v2. So then when you're trying to find the resultant, all you're going to do is add the x's together and then add the y's together. So in this case, u1 of this guy plus the v1 from this guy is going to be your x coordinate. And then the u2 and the v2 are going to be the direction in the y. So again, we can just show this way. If we want to find the resultant r for this whole guy, well then this amount is just the u from the u1 here plus the v1. And if we want to know how long this is, then it's just the u2 plus the v2. Now, scalar product of the real number k and some vector w would just, it just distributes in. So if we want to know a scalar product, let's say that this k could be any constant, like 2 or 3 or 4 or 10. All you do is just multiply that by both the x coordinate and the y. So if I have a vector like w and I want two of them, 2w, well, then they would just get twice as long. If I had it -3w, then it would just go the opposite direction, 3 times as long as w. Whenever we subtract a vector, what we're really doing is adding the reverse of it. We're adding the negative of it. And so technically what you're doing is you're distributing a -1 through the values of the vector, and then you're just adding those things together. It's just another way of saying, you probably remember doing this. You learned early on when you subtracted that you were, if you had 5 minus 2, you would do 5 and you'd take away 2. And you'd be like, oh, I'm left with 3. But then later on you learned that you could do 5 plus a -2. And then you just go, well, plussing a -2 is like taking away 2, and it gives me 3. So this is kind of like saying the same thing, but technically this is what you're doing when you're subtracting a vector. You're adding the opposite of it. So you're taking a negative, you're distributing it through the vector, and then you're adding that to the other guy. So it looks something like this, where your u1 would then be added to a -1 times the v1, and your u2 would be added to a -1 times the v2, which then looks like u1 minus v1, u2 minus v2. All right, so given u is -1, 2, and v is 6, 3, find each resultant vector algebraically and geometrically. So if we're going to add them together, all we do is we take, again, the first ones and add those together, -2 plus 6, and we get 4. And then we take the second guys and add those together, 1 plus 3, and that equals 4. So the resultant vector is 4, 4. So again, if we were going to show what these look like we would add them head to tail, and then note that the resultant is going to be the one that's coming from here up to there, and that is indeed 4, 4. What about 1/3 v minus 2u? Well, again, all we're going to do is distribute that 1/3 through the v, first of all, and then we'll subtract 2 which will be distributed into the u. So 1/3 times 6 should be 2, and 1/3 times 3 should be 1. The negative 2 times negative 2 is going to be a positive 4. Negative 2 times 1 would be a negative 2. So we have 2, 1 plus 4, negative 2. And remember now we're going to add the 2 and the 4, and then we're going to add the 1 and the negative 2. And when we do that, 2 plus 4 is 6. 1 plus negative 2 is negative 1. And our resultant is 6, negative 1. Again, we could show these two vectors and then show the resultant and show that sure enough it goes 6, negative 1. Okay, now a unit vector is any vector u with a magnitude of 1. That's called the unit vector because we're saying the magnitude of it is just 1. Unit vector is in the direction of the vector, but it's found by dividing the vector by its magnitude such that you get to 1 for the magnitude of the vector. So if the vector was actually this long, well, we divide it by the length of the vector, so that way now it's just a length of 1 in the same direction as the original vector. So find the unit vector in the direction of v equals 3 comma negative 5 and verify that it has a length of 1. All right. So the first thing you need to do is you need to find what the magnitude of v is. In order to do that, we're just going to square both components and then add them together and take the square root. So 3 squared is 9 plus negative 5 squared would be 25. 25 plus 9 is 34. We're taking the square root of 34. So now all we do is we multiply the 1 over that into the other two units. So we should have 1 over square root of 34 times 3 and then also times the negative 5. And after we've done rationalizing the denominator, just to get that square root of 34 out of the denominator, remember we just multiply the square root of 34 over the square root of 34 times each one of those units. And we get 3 square roots of 34 over 34 and then negative 5 square roots of 34 over 34. And if you were to actually go about then squaring both of those and taking the square root, you would find in the end that the answer is indeed 1, which is the resultant that you want it to be. All right, so also just take note of this, that standard unit vectors, the horizontal unit vector is just also called I. Don't get this I confused with the imaginary number I. Okay, this is bold I. Also going to be written I with again that half arrow over the top of it. But the I with the arrow, or I bold I, is 1 comma 0. So in other words, if we were looking at the coordinate plane, it's just a vector that goes out just one unit along the x-axis. And then J, otherwise written as this sometimes, again with the vector symbol over the top, if it's not bolded like this, is just 1 in the y direction. So again, if we had our Cartesian plane, it would be 1 unit looking up that way. This is called the vertical unit vector. This is the horizontal unit vector. So a vector can be known as a comma b, but also be ij. So we could rewrite this as ai plus bj, where I stands for in the x direction and j stands for in the y direction. So a, b then are just the units in front of that. So if I had something that said 2i plus 3j, then we would just know that's a over 2 up 3 vector that we're describing. So again, negative 2 comma 8 could be rewritten as negative 2i plus 8j. 17 comma negative 0.6 could be rewritten as 17i minus 0.6j. Pretty easy. Okay, so write PQ with the initial point P equals negative 2, 5, and terminal point Q, 9, negative 7, as a linear combination of standard unit vectors. All right, so the first thing we're going to do is we're going to find what PQ is. Remember, we're going to subtract Q from P, right? So we start with Q because that's what's at the head of this. We subtract off P. So we start with Q. We're going to take this 9, and we're going to subtract off the minus 2. So look at this, minus 2. And then we take the second, the y component for Q, we get negative 7, and we subtract off the 5, minus 5. And when we do that, we get the resultant of 11 comma, negative 12, which we could also rewrite as 11I minus 12j. So another thing to note here is that the vector known as a comma b can also be written as the magnitude of the vector times the cosine of theta, being, again, the x or the I component, and then the y component or the j component, vector component, can be found by taking the sine of theta times the magnitude of the vector. So let's look at this guy. State the component form of a vector representing the velocity of a plane flying 30 degrees west of north at 400 knots. Then express the vector as a linear combination of standard unit vectors. All right, so look at the drawing we've got here. We've got a plane which is flying at 400 knots. We're told that it's flying 30 degrees west of north. So this would be 30 degrees west of north. And it's wanting us to express this as a combination of standard unit vectors. We know that the theta ultimately here is 120, right? Because we would just add, this is 90 degrees to here, and we add another 30. That would give us a theta of 120. So now our equation was just, we take the magnitude times cosine theta, and we get the x component. And we take the magnitude times the sine of theta, we'll get the y component. So 400 cosine 120 and 400 sine 120. And we get negative 200 and 346.4. Again, we can look to see if these numbers seem reasonable. Does it look like we're going 200 in the negative direction and about 346 in the positive direction for y? Yeah, that looks reasonable. That looks like a reasonable sort of number. We can also rewrite that then as negative 200I plus 346.4j. Okay, what about this one? We've got like a J. Smith's hardware sign here, and we're told that it's a 10-pound sign. It's hanging motionless from two ropes, each at an angle of 60 degrees above the horizontal. Find the tension in each rope. Again, I think it's helpful to draw a picture of the forces that are going on here. So let's do that first. So each of those ropes is at a 60-degree angle, and it's holding up the combined weight. So we can see rope 1 and rope 2 are both holding up here at these 60-degree angles from one another. So another way we could then write this, we want to show the resultant vector. Remember, at the moment, both of these are in standard position, where they're both positioned at the origin. What we need to do is take one of these resultant vectors and put the tail to the head of the other one. And that's what we're showing over this direction. So note, we keep the 1 there. We take the second R2, and we're going to move it to where the tail is connected to the head of the first result, the R1. And when we do that, notice that the x component of this in this direction is balanced by this one in this direction, which makes sense, right? If the sign is being held, this guy is pulling it, wants to pull it this way. Well, this one has to pull it with the opposite and equal amount of force in order for it to be motionless. So it makes sense that the ropes do this. And so in the end, the resultant vector going up is what has to balance the weight vector going down. So we know then that this entire side from here down to here has to be 10 pounds, because that's the amount of tension that the rope has to be pulling upward 10 pounds. And once we have that, we actually kind of know what's going on with the rest of this triangle, because if this is 60 degrees here and this is 60 degrees here, we know that the total measurement of this triangle has to be 120 degrees on that angle. And then since we know a triangle has 180 degrees total, and that this is an isosceles triangle, each of these must be 30 degrees. 30 plus 30 is 60. 60 plus 120 is 180. Now, from all of that information, we could just use the law of sines, right, to get the resultant of R1. Because we know an angle, we know an opposite side, and we know another angle and an opposite side. So we could just use the law of sines here, and we could get an answer. And what you'll get, if you do this rightly, is 5.8 pounds of tension in each rope. Because remember, they're going to be the same amount of tension in both R1 and R2. So again, here's our original drawing that we were showing. And we can show here another way to solve this. each rope has to carry half the load, right, of the vertical force. Why can I say that? Well, because there's 2 ropes and they're equal in all other ways. That means if the weight here is 10 pounds, then that means each rope must carry 5. So we could say that the up force of this rope and the up force of this one must each be 5. Well, now, since we know that, can we figure out what R2 is just from knowing that this is 5 and we have an angle measurement here? Is that not just making use of normal trig functions here? We're going to get to the same answer of 5.8 pounds, right? Sine of 60 degrees has to equal opposite, which would be 5, over hypotenuse, R2, right? And so all you would do is you would multiply this R2 up there, and which would then divide this sine of 60 down below. So it'd be 5 divided by sine 60, and you should get, again, this answer of 5.8 pounds. So this is to show you can answer these questions in a multitude of ways. One other problem I just want you to take a quick look at with me. This is from the exercise 41 on page 293. It says here, determine the magnitude of the frictional force in the normal force when a 20-pound box of nails rests on a 30-degree inclined ramp. I just want to kind of show you how we go about doing these in a physics. This is like a very classic physics problem. So if we have the box up here on the ramp, and we know this angle here is alpha, the force of gravity is pulling straight down on the box. But there is a force of friction that's opposing the box right here, trying to prevent it from sliding down the ramp. Also, the ramp is putting a force upward on the box, which is preventing the box from just falling down further, right? It's holding the box up. So there's some sort of, we call this the normal force, the force of the ramp pushing up against the box, while gravity is pulling down on the box, and friction is pushing in this direction on the box. So since we have all that information and we know this is a 30-degree angle on the alpha, we're able to then, from similar triangles, figure out that if this is 30 down here, we can draw this triangle like this because this is a right angle. This must be 60 here. And if this is 60 here, by alternate interior angles, this must be 60 down here, which also means if this is a 90-degree angle, that this must be 30 right here. Or you could also have gotten that because this is a right angle, so 60 plus 30, this must be 30 up here. So again, you've got all the angles that you need, and these are just 30, 60, 90 triangles here. We can then make use of, again, sine or cosine to figure out what the F force would be and what the N force would be with these angles and with this resultant vector of 20 pounds for the weight. So we would find that force would just be 10 pounds, and the other one would be roughly 17.3 pounds. All right, and we're done with lesson 1. So your homework is to work on numbers 2 through 30 and then 44 through 52, doing the evens on those problems. I don't think I gave you many of the word problems this time, so you're just going to be working on getting the concepts down, making sure you understand how to add and subtract these vectors and the scalars and all of that stuff. So hope it goes well. Let me know if you guys have any problems. Otherwise, I will see you guys soon.